All right. So I'm Logan Ward. This talk covers some work that I've been a part of a team on developing over the past few years on how we can use AI and simulation coherently together to design new materials. And the new materials we're looking at, if you're curious, are called metal organic frameworks. They're like sponges that soak up gases. Very cool stuff, but I'll avoid talking more about the material science. And for the intent of this talk, a lot of this is what I worked on when I was at Argonne. And I was at Argonne up until mid-June of this year. I'm now at NVIDIA, still working on this project. And since I wasn't sure which affiliation to kind of account for most of this work, I removed the branding of both employers off of these slides. So pardon my very ugly background. So with that said, let's dig into it. So the overall ambition for this project stems back to a grievance I've had for a little over a decade now, and it's how we do materials design searches. The way that we did this when I was a PhD student, which wasn't all that long ago, was to enumerate everything we could possibly do for a particular material space and then evaluate all of them. And the slide here, the reason there's a red box is anything that's covered under that box, which is about 2/3 of the calculations of materials we studied, are probably not possible to find anywhere in the universe, just with the way thermodynamics works. And each of those took about 5 CPU hours, which is about 2.5 kilowatt hours, or about 500 grams of coal. So a lot of this is a lot of energy and a lot of resources that didn't really need to happen. So as we've already seen in talks today, like the one on multi-objective optimization, there are great algorithms for being able to do this better. Had we hooked these up to a conventional like genetic algorithm, we could have eliminated some, or by taking a more modern tool set, or at least a different tool set, we could do this kind of search with machine learning. There are numerous machine learning algorithms nowadays going under a handful of names: active learning, AI steering, Bayesian optimization, which all employ this loop that combines both simulation and artificial intelligence machine learning together into the same overall workflow. The AI tells you what to do, the simulation does it and tells the AI, and eventually you can find a material faster. And that's what we ended up doing for this materials design project. We created a application which combines together at least one type of AI with several different simulation codes, such that it can continually generate new materials and then teach the AI to generate them better. Walking into that in a little more detail, the type of AI algorithm we use is a generative model called DiffLinker. You can see that in purple on the left. What it does is invents new materials. And this is actually a number we've quantified. 90% of them are garbage in our first iterations. There are materials that are not dynamically stable. They are not actually a single material, they're two. And we get all of these problems with validation. But the way we encountered that and fixed that problem is by feeding its predictions through a cascading series of filters. First, create using to see if we can assemble them, testing them for dynamic stability with lamps, testing them for our physical property of interest, that ability to absorb gases with CP2K and RASPA, and eventually feeding that data back to the DiffLinker system. And you can see down in the bottom right, the rate at which our system is able to find at least newly stable materials grows with time. The curves there are showing in different colors the different scales of nodes we run on, all the way up to nearly all of Polaris, 450 nodes with 4 GPUs each. And around an hour to an hour and a half, those runs tend to get enough data to retrain the model, to start it, to improve its ability to find new materials. And this is something we accomplished by deploying an application that ran all of these different parts on the supercomputer at the same time. We divided up the nodes into different tasks, and even, as shown in the picture on the bottom left, broke up individual nodes to run multiple tasks together, which is a great thing with Parsl. As we were mentioning earlier, you can have different configuration or for different parts of your application. And those we could have anything from single CPU core to a dozen GPUs all under the same. So 2 minutes. So now I can go to my gripe slide. This wasn't very easy. There were a lot of things about building this application, some of which were Parsl, some of which were other problems that made not just constructing it in the first place, but making it run on dozens of nodes to hundreds of nodes to actually several thousand difficult. My Parsl config file is 200 lines long in order to achieve that. And that's not something I say proudly. It's something that I say just to illustrate that there are a lot of things we've done here that are special. And if these are things which we see used in more applications, really there's some documentation improvements we can make, sharing out these examples, removing as much cruft from mine as possible to make it something that's a real learnable instance. That'd be something that I'd be glad to do. Additionally, we ran into problems on sending massive amounts of data between nodes because all of the data from each task has to get routed through the Parsl DFK. This could very much, and we've seen this, saturate the Parsl central process, reducing its rate at which it can coordinate workers. That limited our scaling to about 2,000 nodes on Aurora. And additionally, we had the ever-present scientific codes that do not have dependencies which are modern or which agree with any others. And that's something that we've been studying how to do more often. For the two parts, the massive configuration file and streaming issue, not me, but colleagues at the University of Chicago have been exploring how we can disaggregate that single Parsl workflow into a more manageable agentic style workflow. Not my work. You're going to hear more about this one later. I think tomorrow Greg is talking about it, but I wanted to hype it nonetheless. And the second is I'm studying which ways that containerization can help us out. Whether we can package our AI components as containers, containers built against the NVIDIA blueprint, using that garden technology that you heard about from Will, all of that can hopefully make it better. So I'll go back to my complaint slide and leave that one up if there are any questions.